Hello and welcome to Class 6. We're going to cover sections 3.4 through 3.7, and these involve equivalence calculations using the effective interest rate. And of course, that's the only interest rate that you can use to do these calculations that involve moving money around in time. So we're going to discuss how do we get the right time period and the right effective interest rate today. I'd like you to read in the ebook or the smart book pages 86 through 94. This video that we're recording right now will be uploaded to Blackboard under Contents in Module 3 or Chapter 3. And finally, these lecture notes will also be uploaded at that site. I want to go back and pick up something that I missed in Class 5, and that was one more. We talked about the effective interest rate formula when you knew the nominal rate and the number of compounding times, which was equation 3.2. In the case where interest is not compounded, excuse me, where the interest is not compounded at different points in time, but is continuously compounded, you get to equation 3.3. And that should be a 3 there. This is equation 3.3 is correct. And that formula is I is equal to E to the R minus 1. Not R minus 1 this is a minus 1 after the E to the R. And whatever period you want the I for, that R, the nominal rate, has to be for that period. Just like equation 3.2. This equation can be derived essentially by letting the number of compounding points in time in equation 3.2, which was M, letting that number go to infinity and taking the limit. So we will use this in some of the problems, homework problems, and other cases involved. So the next thing I want to do is move on into section 3.4, which is equivalence calculations when only single amount factors are used. We had a single compound amount factor when we're trying to find a future value if we know the present value, and we have a single payment present worth factor if we're trying to find the present worth but we know the future value. Those are basically given here in equation 3.4 and 3.5. And the key is that the rate that you use in the formula has to be the effective rate, and that has to be the number of periods. Now, the reason the author breaks this out into a separate section involving only single payments is because you have more flexibility in deciding what period you're going to use. But when you have a series of payments, your flexibility goes away because the time period between the payments defines your time period. When you have just single payments, you can use alternative time periods depending on which you prefer. And I'm going to give you an example of how we would do that. The example says, suppose you wish to find a future value at the end of year 6 of $1,000 deposited at the end of year 2. The interest rate is 8% per year compounded quarterly. Okay, so we're looking for the future value at the end of year 6. We're depositing the money at the end of year 2, so we would have to take that money from year 2 to year 6, so that would be 4 years into the future. So we could use years as our time frame, or we could say, oh, but we're compounding quarterly, so I know that the nominal annual rate is 8%, which was given here. That's the nominal annual rate. But since it's compounded more than once a year, that's not the effective annual rate. So if I use annually, I will have to find the effective annual rate. But if I use quarterly, in other words, from the end of year 2, which is quarter 8, to the end of year 6, there would be 4 years, but that's 16 quarters. I could use a quarterly interest rate. And actually, the quarterly interest rate's very easy to get. I mean, I know it's 2%, but I don't recommend that you do that. Just go ahead and use the formula. The quarterly rate, I quarterly, is equal to 1 plus, this should be I quarterly, 1 plus the nominal quarterly rate divided by m to the m power minus 1. But R quarterly can be gotten from R annual and divide it by 4. So that's 2%, and m is 1 because it's compounded quarterly. So I quarterly is equal to 2% because it's 1 plus 0.02 divided by 1 to the 1 power minus 1, which is 2%. And so I quarterly equals R quarterly because m is 1. That is because it's compounded once every quarter. The next thing we will do, now that we know that our quarterly effective interest rate is 2%, and we know there are 4 years or 16 quarters between when we deposited the money and when we want that future value, then we just plug into our equation. The future value is the present value times find f given p at rate I for n periods. Now this I is the quarterly rate. That has to be the number of quarters. So this will be 1,000 f given p, 2% for 16 quarters. If you crank through that, you'll get 1373. I could have just as well said, oh, that's 4 years. Let's use the effective annual rate. So if we want to get the effective annual rate, I annual, it's equal to 1 plus R annual divided by m to the m power minus 1, which is 1 plus 0.08 divided by 4. That's my R annual is 0.08, and m is the number of times it's compounded during that period for which I have the R, which is quarterly is 4 times a year, so that's 4 to the 4th power. So that becomes minus 1, then 1.02 to the 4th power minus 1, which turns out to be 0.0824 or 8.24%. So now when I plug into the future value equation, I take the present value, f given p, the interest rate is the annual rate, this is the number of years. So I crank through that and I get the same answer. I must get the same answer, of course. But this is because I have just a P and an F. If you have a series, an A series, or an arithmetic gradient, which is a capital G series, or a geometric gradient, which is a small g series, you cannot do that. You must use the period that the cash flow occurs in. So if it was a quarterly cash flow, you'd have to use the quarterly rate. So section 3.5 covers the case where you're trying to find equivalent calculations, but you do have a series of cash flows. You have either a uniform series, an arithmetic gradient, or a geometric gradient. And that series, the time frame between those payments in that series will define the needed time frame. So we don't have the option of using quarterly or annual like we did when we just dealt with a P and an F. So we're going to give an example of how you can do that as well. Suppose you wish to find the present value at time 0 of a cash flow of $100 every quarter for 5 years. So this is going to define my time period. It's quarterly, okay? You are also given the interest rate is 12% per year compounded monthly. Now I have monthly compounding and I have quarterly cash flows. So which is the payment period is quarterly, the compounding period is monthly. So we're in this condition of section 3.5. The payment period is greater than the compounding period. Compounding period is every month. The payment period is every quarter. So in this case, we have to find the effective interest rate for the period between the payments. So the payments are quarterly. I need the quarterly effective interest rate. So I'm going to go there and get I quarterly is equal to 1 plus R quarterly. Again, the time frame for this I always has to be the same as the time frame for that R. This is M is the number of times it's compounded in the period for R to the M power minus 1. This is equation 3.2 again. We're using it repeatedly in this chapter. But first we have to find the R quarterly. We were given 12% per year compounded monthly. Well, the quarterly rate is just to divide the 12. The nominal annual rate is 12%. It's not the effective annual rate because I'm not compounding just once a year. So the nominal annual rate is 12%. So I take that, divide it by 4 to get the nominal quarterly rate. So now I have a nominal quarterly rate which I need for this equation. And when I plug in I quarterly then is 1 plus R quarterly divided by M. R quarterly is 0.03. M is the number of times the interest is compounded every quarter. Well, there are 3 months in every quarter, so I divide that by 3, raise it to the third power minus 1, and that turns out to be 3.03%. See, my quarterly nominal rate is 3%, but because I'm compounding more frequently, I end up with an effective quarterly rate of 3.03%. So now I have quarterly payments of $100 a quarter for 5 years, so there's 20 of them, and I have an effective quarterly rate. So my present value is the uniform annual series amount, A times P given A, I, N, and this is dollars per quarter, $100 per quarter. P given A, this is the quarterly effective rate, 3.03%, and this is the number of payments and also the number of quarters. So when I plug this in and use my calculating app, I get $1,483.63, or 14 should be 84, I believe, if I did that right. And we'll go on into then section 3.6. In section 3.6, we're involving equivalence calculations where you have a series of payments, and the payment period is less than the compounding period. This is the opposite case of section 3.5. And the author has an example, 3.6, where he has a cash flow that looks like this, where the horizontal scale is in months, but the interest is compounded quarterly. So let's put in the compounding points. There's a compounding point at 3 months because that's the first quarter. I'll just put a 1 there. There's a compounding point at 6 months, because that's the second quarter. There's a compounding point at 9 months, that's the third quarter. And then there's a compounding point at 12 months, that's the fourth quarter. And also, there's a compounding point, of course, back here at time 0. And so, what you do in this case, where you have payments more frequent than the compounding points, so that the time between the payments is less than the time between the compounding points, you move the money. The author basically says we're going to assume 0 interest between these compounding points. And that really isn't 100% correct, but it's our best bet to work with the money we're working with right now. Excuse me. So, what we're going to do is the negative cash flows are brought forward to the next compounding point. So this $200, I'm going to bring it forward to the end of month 3 or compounding point 1 there, and I'll take this away and put the 200 there. The next 2 negative cash flows, one is at time 4, I'm going to move it over to time 6, and then I'll move this one over to time 6, this $100 at time 5, and then at time 6 I will have $175 negative. Then I'll go and look for all the negatives. There's a negative at time 10, and the next compounding point is time 12, so I'll move this $50 over here to time 12, and that'll be there, and move it from there. We want to know the future value at the end of the year, so that's the unknown. We'll put that F is equal a question mark there. Now that we've moved all the negative cash flows forward, we move the positive cash flows backward to the prior compounding point. So this $90 will come back, and it'll be right here at compounding time 2, that's $90. The next positive one is a $45. Well, the next one is $120, but it's at a compounding point, so it does not move. And then the next one is the $45 at time 11, month 11. It goes here, and it gets added to the 120, so now I'll have 165 here. And that's it. So now we're going to work with this cash flow, which is a quarterly cash flow, and we have quarterly compounding. And what we'll do is take these to the future, because this is a series of cash flows, but it's not a uniform series, it's not a gradient series. We'll have to take these one at a time to the future. And so that's what I'm going to do in the next calculation. First of all, I'm working with quarters, so I have to find the effective quarterly rate. Well, the nominal quarterly rate is the nominal annual rate divided by 4, so it's 3%. The effective quarterly rate is I quarterly is equal to 1 plus R quarterly divided by M to the M power minus 1. But R quarterly is 3%, but it is compounded once per quarter, so M is going to be 1, so everything's going to fall out, and R is going to equal I quarterly, 3%. Mentally, if you get used to this, you realize this is quarterly compounding, so I quarterly is going to be equal to R quarterly. That's fine. You don't have to go through this tedious step of plugging it in. But until you get to that point, I think you should go ahead and always use equation 3.2. That's what we're doing. This is equation 3.2. This actually is equation 3.1. So we will now solve the problem taking each of these cash flows to the future, the first cash flow was at a compounding point. I didn't even talk about this one. That's the $150 here. This is going to go forward. That's a negative 150, by the way. It's going to go forward 4 quarters and at the rate of 3% per quarter. So we will have minus 150 F given P, 3% for 4 quarters. The next cash flow is going to be at time 1, and remember we moved this $200 over to the end of quarter 1, so because it occurred inside quarter 1, and the negative cash flows get moved forward, so that one will be at time 1. We want to bring it over to time 4. So we're going to bring this cash flow 3 quarters forward, and that is minus 200 F given P, 3% for 3 quarters. The next cash flow is at the end of the second quarter, and here we had a minus 175 because we brought these two over, and we had a plus 90 because we brought this one back, and that's going to give you a net of minus 85. So the net value minus 85 is taken forward, F given P, for 3% for 2 quarters. And then finally, not finally, because we have one at time 4, but at time 3, third quarter, we had 120 right at the quarter, and we brought a $45 back, and that gave me 165. Added the 45 that I brought back to the 120 that was there, and that gave me 165. And so I need to bring that forward at 3% for 1 period. And then finally, there was that $50 here. It's a minus 50 that I brought forward to time 4 because it was in the middle of the 4th quarter there, and the negative cash flows get brought forward. So that's the minus 50. And then if we calculate all these factors and go through it all, we end up with $357.60 plus 82. But I kept these decimals because the author said that those numbers in this figure are really in thousands of dollars. So to get the actual future value, I have to multiply by 1,000. So when I multiply this $357 times 1,000, I get $357,000 and $608, and that's the answer to this particular question. Section 3.7, the last section in the chapter, just deals with using Excel to find the effective interest rate. Remember, the way we find the effective interest rate is by equation 3.2. And so there is an Excel function which says equal effect, and then you open parentheses and you put in the nominal rate and how often it's compounded, and it will return in that same cell the effective rate. It's not much of a calculation, but you can do it by hand or you could do it in Excel. The next thing I'm going to do is work a homework problem. Now this is problem 5 when I accessed it, but it may not be problem 5 when you access your homework. But it will be one of the 10 homework problems that's at the end of chapter 3. Sorry. And so let's go through this problem. Ellis Autotrol Inc. plans to install an eco-friendly energy recovery system that will cost an estimated $86,900 if it is installed 5 years from now. So this is a future value at the end of 5 years. the company uses an interest rate of 10% per year compounded continuously. So remember that equation 3.3 that I presented at the very beginning of the lecture in red here is I is equal to e to the r minus 1. So we're going to need that particular equation 3.3 to work this one because it's a continuous compounding. Continuous compounding is actually easier than discrete because with continuous, your compounding period is always shorter than your payment period. So so the question is, how much is the present worth of this $86,900? So we're dealing with continuous compounding, and so we're going to find the effective annual rate, and where the nominal rate is 10% per year. And so we use equation 3.3. I annual is equal to E annual minus 1. And E annual is 0.1 minus 1 gives me 0.10517, etc. And then if you take that as a percent, it's 10.517%. And then the present value then will be the future value, which was the $86,900. The interest rate is 10.517%, and the number of periods is 5. So when I plug in that, this would be this number to the minus fifth power. I could either use, I use the algebraic formula here. You could use the symbolic formula and go to your app. I got $52,708. And that concludes this class number 6.